The third corollary to the mean value theorem states that on intervals where my function is increasing, going up from left to right, the first derivative is positive. And on intervals where my function is decreasing, going down from left to right, the first derivative is negative. More formally, suppose that f is continuous on the closed interval ab and differentiable on the open interval ab. If f prime of x is bigger than 0 on the open interval ab, then f is increasing on the closed interval ab. If the first derivative is less than 0 on the open interval ab, then f is decreasing on the closed interval ab. So if I look at this first diagram, I can see a spot here where the first derivative is equal to 0. On this side where my function is going up from left to right, I see positive slopes, positive little tangent lines, decreasing in value until I get to the top. And on those positive slopes, my function is going up from left to right. On the other side where my function is going down and decreasing from left to right, I see slopes that would be negative. In this next diagram, I see a spot here at the top where I have a cusp and my first derivative is not defined, but on this side, I see positive little tangent lines, and on this side, I see negative slopes. And those correspond to where my function is going up from left to right and going down from left to right. And even in this last picture, where again here, I see my function going up from left to right and a slope of 0, and then down from left to right, I see positive tangent lines that get steeper for a while and then level off, and then the same thing but mirrored here with the negative tangent lines. But still, where they're positive, my function is going up from left to right, and where the tangent lines have negative slope, they are going down from left to right. So, if I know the signs of the first derivative, I'll know where functions are increasing and where they are decreasing. Now, the third corollary to the mean value theorem tells me that I am either increasing or decreasing on a closed interval. And if I look at any little interval over here, AB, where my first derivative is positive, I'm increasing from an endpoint to an endpoint. Most often we're asked to identify open intervals where a function is increasing or decreasing, kind of thinking of that largest collection of things where my function is going up from left to right and down from left to right. So let's work an example. Find the open intervals on which f of x equals x cubed minus 12x minus 5 is increasing and decreasing. Now, in this section, we're also introduced to a new term. Those intervals where my function is either increasing or decreasing are intervals where my function is called monotonic. It has one behavior. It's either increasing or decreasing. So another way of thinking about this is we're finding intervals on which this function has monotonic behavior, where it's either increasing or decreasing. But thinking about that third corollary to the mean value theorem, let's take a derivative and see if we can figure out where that derivative is positive or negative. So there's my first derivative, 3x squared minus 12. And what I need to do is figure out where that derivative is either bigger than 0, that will be where my function is increasing. I need to figure out where it is less than 0, that will be where my function is decreasing. Well, what I'm going to do to start is think about where my first derivative is actually 0. And as I solve this equation, I find out that I'll have zeros when x is either plus or minus 2. So I'm going to think about the signs of my first derivative on a number line. Because these are the spots where my first derivative is actually a 0. You plug those in and you get 0. If I think about what I've seen so far with critical points, those are spots where I might have a min or a max, a local min or a local max. This function doesn't have any spots where the first derivative is undefined, but I think those are going to be important for us too. But let's just see if we can assign a plus or a minus, figure out where my derivative is positive and negative. I could think about the graph of 3x squared minus 12. If I think about this as the x-axis, that's an upward-facing parabola. On this part, it would be positive because the graph of that parabola is above the x-axis. In the middle, this should be a negative because the graph of the parabola is below the x-axis, and then plus again for the same reason we had over here. But another way of solving polynomial inequalities like this is to plug in sample points. So on the ends, I think we should use 3 and minus 3, and in the middle we should plug in 0. And whatever sign we get out for these sample points, that will be the sign of the whole interval. So, minus 3, we plug that in. Minus 3 squared is 9, times 3 is 27. Minus 12 is 15. The important thing is that it's positive. Plug in a 0. We'll get out minus 12. And then plug in a positive 3, and we'll get the same thing we got over here, assuming I did all that arithmetic correctly. Regardless, I'm sure it's positive. Okay, well, where the first derivative is positive, my function is going up from left to right. So on both ends, my function is going up from left to right. And in the middle, my function must be going down from left to right. So the intervals on which my function is increasing. Well, I'm increasing from minus infinity to minus 2 and from 2 to infinity. I'm decreasing between minus 2 and positive 2. Now, one thing I want to point out is I didn't put a union symbol between these two places because that would say that no matter the 2 points I ever picked, whether they were one was in here or in here, that they were always appeared in the order that the left one was lower than the right one, and that might not be true. We don't want to put a union symbol between these two pieces where my function's increasing. I don't know what the exact shape of this graph is, but I know that cubic functions sometimes behave like this. And I could very carefully pick an x in this first part that was higher than an x in this part. So what I'm saying when I list these two things is that if I take 2 consecutive x's in this part, they're going up from left to right. And then if I take 2 x's in this part, they're also going up from left to right. Most often I don't even use an and. I'll just put a comma between the two intervals where I have increasing and then increasing, making no claim about whether this piece is always higher than that piece. All right, so intervals on which my function is increasing, the first derivative is positive, and intervals where my function is decreasing, my first derivative is negative.